everyone. In this presentation, we delve into the fascinating realm of unsupervised learning applied to molecular data, showcasing how it can empower us to achieve improved clustering and uncover emergent properties within chemical compounds.
So first, let's zoom into the broader vision we've set our sights on, the creation of a language model that instills fluency into our comprehension of molecules. This slide outlines how this aspiration aligns with the strides we've made through our research. In biochemistry and pharmacology, understanding molecular structures and properties is essential for innovative drug discovery and scientific progress. However, retrieving these insights from databases has its own challenges. For example, existing databases often lack efficiency and user-friendliness. Well, our research introduces a paradigm shift. We focused on crafting an embedding model tailored for SMILES data. This innovation isn't just about supplementing databases, it's about replacing them with a model that communicates fluently about molecules. This model, as it evolves, strives to comprehend and articulate molecular intricacies that just as seamlessly as human language. The crux lies in the model's ability to process not just encoded data, but natural language itself. This means we're moving beyond conventional databases, envisioning a future where queries and insights happen seamlessly through knowledge and language.
This project has two goals. One, to train an embedding model using LLM vector search to take in natural language and replace standard molecule databases. And two, to train our own embedding model for the unique structure of SMILES data and give the model two chances to develop emergent properties. Some background information. Vector search is a method of finding similar items based on their characteristics or features. Frequently used for semantic search, vector search finds similar data using approximate nearest neighbor algorithms. SMILES data stands for Simplified Molecular Input Line Entry Information, and it's a way of taking in the structure of a molecule and encoding it into a single line using standard characters. We also use a type of vector known as embeddings, which are numerical representations of objects and relationships expressed as vectors. Embedding vectors that are close to each other or far away from each other can be considered similar or different, respectively.
For data collection, our group utilized the PubChem's record description dataset, which only contained chemical compounds with descriptions and a size of 328,000 compounds. As a result, we were able to work with chemical compounds with descriptions that were suitable as reliable training data for a large language model. We then utilized PugView to access the description data from every source on each of the compounds. This was compiled into a dataset containing the descriptions, the SMILES data, the molecular weight, the chemical formula, and other information on each one of the compounds, yielding a sizable dataset for our research. At the end of our data collection, our dataset contained an average length of 3.09 sentences per description. Ideally, to increase the average length, you can use ChemCrow, a method which can derive richer descriptions using online queries for information, which will be discussed later. Next, we discuss our methods in regards to data enhancement. Our first method for data enhancement was creating a web scraper, which works by extracting important information about target molecules from respected scientific journals and adding it to the descriptions. But this method would require extensive custom queries with the Google API, which is both expensive and time-consuming. Instead, we concatenated the description data with the other categories in the dataset, such as molecular formula and polar area. As a result, the average length of each description increased with important information. For example, instead of a description classifying a certain molecule, it could say the molecule contains X number of carbon or oxygen atoms.
Moving on to methodology, graph neural networks. First, GNNs are a neural network that processes and analyzes data in the form of a graph, with nodes and edges between, representing nodal relationships. Take a look at the first picture for a visual representation of this. We used our GNN to both enhance the dataset by increasing descriptions and as a benchmark for property prediction performance in the LLM, which will be discussed later. Our GNN uses SMILES strings as graphs to predict blood-brain barrier permeability of molecules. The blood-brain barrier is a highly selective and semi-permeable boundary that separates the circulating blood from the brain and its surrounding extracellular fluid. Thus, the permeability of certain molecules is vital information in developing drugs meant to target the central nervous system. To predict this property, we utilize the message passing neural network MPNN model detailed by Karas. The MPNN is trained on the benchmark dataset with 2,050 molecules. The model takes in smile strings and turns each into a molecule object using RedKit, and then returns a graph represented in the form of a 3-tuple. Take a look at the second picture. The model reported 96.28% accuracy on predicting permeability after training and a 90.26% validation accuracy after testing. Finally, we took the PubChem dataset and ran the smile string column through the MPNN to get permeability predictions for all 328,000 molecules. We then needed to convert the output float values into natural language descriptions, which we did by running the outputs through an algorithm that assesses the value and returns the permeability as a string sentence. For example, 2,3-dihydroxy-3-methylpentanoic acid predicted a permeability of value 0.02 on a scale of 0 to 1. This result was then turned into the string, "This molecule has a very low blood-brain barrier permeability." These descriptions were then concatenated to the molecule's respective descriptions already in the data frame.
This next section of the project covers using large language models to discern properties in molecules from large language prompts. The two main models we used for fine-tuning were Llama 2 and OpenAI's Curie model. The main differences are that Curie is run completely externally and is API-based, while Llama 2 is run locally, which makes it more computationally expensive. Curie is more expensive to fine-tune. Curie also has 13 billion parameters to Llama 7 billion, which makes it a deeper network.
Our initial strategy was to fine-tune both Llama 2 and Curie using textual descriptions. However, this approach didn't quite deliver the optimal outcomes we were aiming for. Realizing the need for a new approach, we decided to input just the smile strings of molecules as prompts. This shift seemed promising, although it had its own set of challenges. Interestingly, the LLM faced difficulty in grasping the subtleties within those smile strings, which revealed a limitation in their understanding. To overcome this, we formulated a natural language prompt using graphical data from smiles. This involved leveraging the RDKit library to extract meaningful insights from the graphical representation. The results were pretty intriguing. Initially, our accuracy rested at 50%, which is not particularly impressive. However, as we honed in on more specific data, focusing solely on blood-brain barrier permeability, the accuracy surged to 71%. However, around 90% of predictions were constantly outputting 1, regardless of the actual value being either ones or zeros. While the model's accuracy improved, this questioned whether the model truly understood molecular composition or whether the skewed pattern could be a result of luck.
In an attempt to create a better representation of the graphical data, we created an adjacency matrix, or a graphical representation of a molecule given smiles input, and used that as a prompt to fine-tune the model with blood-brain barrier permeability as a completion. This yielded suboptimal results, and it showed that word-based transformers have a hard time understanding graphs represented in text form. And as a result, graph-based transformers would be a good step moving forward to create a model with improved understanding of a molecule. We also fine-tuned Curie on the data derived earlier from scraping PubChem to create an LLM that could understand molecular groups and their properties. Compared to the approach using embeddings stored in a vector database as context for GPT, which is discussed later on, it is faster and cheaper. With the current data, it is not as accurate, but with a scaled approach and more heavily curated data, it can become a great method for understanding molecular properties and their relations. Next, we move away from using large language models and look into using embedding models. The 5 main embedding models we used were 3 based on BERT, 1 based on OpenAI, and 1 custom embedding model using SimClear, which is discussed later. OpenAI embeddings cost some money and had a much higher dimensionality, which made them difficult to work with computation. We ended up settling on using BERT embeddings as the main embeddings we used. We put them into 2-dimensional representation using TSNE and visualized them, as you can see on the figure on the right. These embeddings were stored in a vector database and given as context to GPT 3.5 Turbo. To generate benchmark data, we scraped Wikipedia for the descriptions of the molecules and use a rephrasing model to prevent GPT from relying on its vast knowledge of Wikipedia. At first, we told the model to find a given molecule given the description as a question. But a problem arose because each question can have multiple answers, making a flawed benchmark. Instead, we query the model to generate a description given a molecule to see if it can understand different molecules and their properties. We compared this result to the Wikipedia data via cosine similarity to compare the semantic meaning. Overall, the GPT model with the vector database as context performed better according to this similarity metric.
The SimClear architecture is a powerful deep learning framework designed for generating meaningful representations from raw data. We utilize SimClear to create embeddings of RDKit Morgan fingerprints derived from SMILES data, which encode molecular structures. SimClear employs a Siamese network structure where two identical subnetworks share the same weights. It learns by maximizing the similarity between positive pairs while minimizing the similarity between negative pairs. We use the cosine similarity loss function to do this in our case. This process encourages the network to learn high-level features that capture the intrinsic structure of the input data, making it well-suited for the generating informative embeddings of the molecular fingerprints. These embeddings can be valuable for tasks such as molecular similarity analysis, compound screening, and drug discovery, as they encode the underlying chemical properties and relationships between molecules in a continuous vector space. Here you can see a visualization of the SimClear embeddings made with TSNE.
Acting as a search engine, the vector search algorithm uncovers structural similarities in molecular data, such as rings and ring-adjacent structures within given molecules. Utilizing one-hot encoding and TSNE, embeddings capture data relationships, forming the foundation for analysis of these very structures, as well as molecular properties given data about clusterings of such properties, such as functional groups and reaction stability. The cluster reaction adapts dynamically via affinity propagation algorithms, enabling pattern-based grouping without a set number of clusters, as is given by the k-means clustering algorithm. This segues into RDKit enhancing molecular fingerprinting. By incorporating SMILES data and pre-encoding for precise chemical assessments, RDKit helps create fingerprints for unique molecules, which gave us ample ability to cluster and embed such said molecules within the context of our project. Finally, the algorithm employs the Mahalanobis distance metric to identify quote-unquote similar molecules, considering the data shape, size, and variable relationships. The Mahalanobis distance metric computes the smallest distance from a query point to the molecule distributions, revealing similarity properties tied to structural relationships between molecules. Above is accuracies for a model given on the left, with random chance variables given on the right. Our model provides much better accuracy given the threshold of 0.5 as our Tanimoto coefficient against a random cluster. The model clearly describes how, with the given correlation coefficient, our model gives much higher accuracies when compared with a query of random molecules. This describes structural similarities within molecular structures. Here are our results for the vector search algorithm. The blue point represents the center of a given data cluster, while the scattering of points reveals the embeddings of the molecules. The clusters of molecules each represent unique orderings powered by molecular fingerprinting. Given the Tanimoto coefficients, they represent the similarities between a chosen molecule and the others in the cluster. The Tanimoto coefficient acts as our benchmark for the accuracy in the given model, as elaborated further in our results section. In the future, the embeddings of our molecular fingerprints can be used to calculate the distances to the cluster, assisting in easy drug development as well as drug customizability. And as you can see, most of the Tanimoto coefficients lie between an accuracy level of 0.7 and 0.97, which indicates high relatability. Here, the structural similarities are very clear between an amphetamine molecule and methylhethylamine molecule. These molecules are classified as neurotransmitters and have a similarity in their structures as given by the ring adjacent structures in the pictures above.
The Tanimoto coefficient is a similarity metric commonly used to quantify the degree of overlap between two sets. It is calculated as the ratio of the number of shared elements to the total number of unique elements in the sets. In the context of chemistry and molecular informatics, the Tanimoto coefficient assesses the similarity between molecular fingerprints or descriptors where sets represent binary substructure patterns. A Tanimoto coefficient of 1 indicates complete similarity, while 0 signifies no common elements. This coefficient is widely used in tasks like drug discovery and chemical database searches to gauge the structural resemblance between compounds and aids in making informed decisions based on shared features. Overall, we got pretty favorable results, getting coefficient scores primarily between 0.7 to 1 from different molecules in a cluster generated by the vector search algorithm.
As discussed earlier, for the GPT model with the vector database as context, the benchmark involved scraping descriptions off Wikipedia and summarizing them using the Hugging Face model. The LLMs were then prompted with generating a description using the knowledge it has about molecules and their properties in the test dataset, which is not included in the embeddings. And this output was compared via cosine similarity between the LLM output and the Wikipedia description. This found the semantic overlap and how much of the LLM generated description overlapped with the Wikipedia description. As you can see on the figure to the right, the model with the vector database as context performed better than the base GPT model with the same prompt engineering methods as input.
Incorporating a large language model with the capacity for emergent chemical fluency marks a transformative leap in scientific capabilities. This augmentation empowers the LLM to not only comprehend chemical intricacies, but also to harness this understanding for the creation of novel molecules and pharmaceutical compounds. The implications of this concept extend beyond the boundaries of conventional research, as it enables the simulation and evaluation of these synthesized entities well before any physical realization. This exploration encapsulates a grand-scale notion that could revolutionize the landscape of drug discovery and molecular design.
Finally, what will be our future work? As this project wraps up, we want to explore some last few methods to optimize results. Quality data is crucial for successful embeddings. They should be extensive, have variability, and non-redundant. For data enhancement, we want to investigate ChemCrow's capabilities in obtaining richer descriptions through online querying. ChemCrow is an LLM chemistry agent designed to accomplish tasks across organic synthesis, drug discovery, and materials design. For our LLM, we want to train a larger and better pre-trained model to increase the accuracy of our results, as well as explore graph transformers in understanding SMILES data as LLM prompts, which previously presented an obstacle in BBBP property prediction. Graph transformers can turn graphs into the vector space that LLMs use and get rid of the requirement for the input data to be strings that would make it easier for pattern recognition. Lastly, we want to generate more diverse data for the fine-tuned LLM. Finally, we will create a search engine to increase accessibility and reach of the LLM, which was ultimately one of the primary objectives of this project.
Thank you for listening to our presentation. We would like to acknowledge Blast AI for giving us our beautiful mentor, Saurabh Kumar, and PubChem for our datasets. We'll gladly now answer any questions you may have.